So welcome to our discussion on thermal energy. We're going to discuss what thermal energy is and how this might differ slightly from concepts of heat and temperature. When we're talking about thermal energy, we usually care about how it relates to either solids, liquids, or gases. If we look at the arrangement of molecules in these three states of matter, here is a solid with a regularly spaced lattice. In this particular case, this would have relatively low thermal energy. When we apply thermal energy to a solid, or increase its temperature, apply heat energy to it, what we're going to do is provide increased energy for each of these molecules. That will cause these molecules to vibrate, rotate, and also translate. Now, by translate, that will give it the energy to move around. Consequently, if we're looking at something, say like water, it will form a solid lattice when it is in the ice phase. As we provide heat energy, as we provide thermal energy to this system, each of these molecules starts to gain a greater kinetic energy, and therefore a greater velocity, and they start to move around. Essentially, this material will melt and flow. If we continue to add thermal energy to our system, the particles in the system will start to gain progressively more thermal energy and progressively more velocity and kinetic energy. That means you can then make the transition from a liquid, which essentially flows, to a gas, which can move around in three full dimensions here. And as you can see from the vectors here, these vectors here are representing the velocity of the particles in this system. As a solid, these molecules will be relatively stationary. As a liquid, they gain the energy to move around and interact with one another. And as a gas, they gain much more energy, much higher velocities, and much higher average thermal energies for each of these particles. So we really want to look at thermal energy as in how much energy is provided to the particles in our system. And that's where temperature becomes important and relates to the dynamics of a system. So when we're looking at the system we just talked about, at a low effective temperature, that's what TF represents here, we're looking at the atoms being constantly spaced, but maybe still vibrating a little bit or rotating just a tiny bit, but not really flowing over one another. As we end up vibrating them more, providing more energy to each of these molecules, they'll vibrate more, they'll go into higher vibrational states, and you'll end up with them spacing out a lot more. They'll start to move back and forth. And then once you reach higher effective temperatures, they will eventually start to flow over one another and gain enough energy to move with their own specific velocity relative to their neighbor. So, we can really relate thermal energy and temperature to the dynamics of our system, how much energy is provided to the particles to move around. So that means we can think of temperature as the average kinetic energy of all the particles in our system. So thermal energy really is a measure of the kinetic energy of the collection of particles that we have in our system. Higher temperature means more energy is available to those particles to move around. So the thermal energy of a gas can really be described as how much kinetic energy is given to the individual particles in that gas. So what we mean by this is here are two systems, essentially a sealed box such as an oven or something like that, and the particles within this gas have a specific velocity. So cast your mind back to vectors. Here we have small velocity vectors. Kinetic energy is half mv squared at its core for an individual mass. That means the kinetic energy of this particular particle relates to its velocity by half mv squared. Over here we have the same system now with the same gas molecules, but the thermal energy here, the temperature, has been significantly increased inside the oven. This means that these particles have much more freedom to move around and are doing so much more quickly. And as you can see, some of these are bouncing off of the walls, and every time they do, they'll translate a little bit of their energy to the walls of the container. So this is why if you touch the side of something like an oven, you'll find that it's hot. That's heat energy, that's kinetic energy from these particles being translated into thermal energy to the walls of the oven. And that's kind of an inefficiency if you're trying to heat up the particles inside this particular container. This is also one of the important things in things like chemistry. So if you start a chemical reaction, if you apply heat to that chemical reaction, it usually makes it go faster. That's because you're increasing the kinetic energy and velocity of the individual particles and increasing their interactions. These particles are much more likely to start bouncing off one another and the walls much more rapidly here than they are in this system at lower temperature. So when we talk about thermal energy, there is a dependence on the density of the system. So our thermal energy is the total kinetic energy of all the particles in the substance. And that means you have to think about this in terms of density. So here we have a high density, low temperature system. This has more thermal energy than the system we have here, which is a low density and high temperature. So even though this oven is at 400 Fahrenheit and this pan is only at 212, we end up with less thermal energy here because there are less particles in the system. So when you count up the thermal energy of all these individual particles, you'll end up with a lower energy than you will here, where you have more particles. So temperature is not always a direct gauge of thermal energy. If you're confused, think about this situation. If you go into low Earth orbit, you will require a spacesuit. Let's forgo the idea that you need oxygen here and just think about the temperature of the astronaut. If you were to leave a heated spacecraft without a spacesuit, you'd be immediately flash frozen and severe tissue damage would result and you would die. This astronaut is wearing a spacesuit here. This is actually Ed White leaving the Gemini capsule. He's wearing a spacesuit and operating quite effectively in low Earth orbit. Low Earth orbit actually has quite a high temperature of about 10 Celsius, or if you translate it to Fahrenheit, a unit I'm not a particular fan of, about 50.3 Fahrenheit. Now these are temperatures that the human body can obviously stand, and this is the temperature that he's currently in. But due to the extremely low atmospheric density, he would be immediately frozen because there's very few molecules around him. The density of the atmosphere at low Earth orbit is extremely low, so there's not much thermal energy. And it was this that really fascinated people like William Thomson, or as he became known, the first Baron Kelvin, born in 1824 and died in 1907. Now, Kelvin spent a lot of time looking at things like electricity, and he also, of course, as we'll come to, looked at the first and second law of thermodynamics. He was actually an electric telegraph engineer and invented a lot of different electrical items, and that's what made him rich and famous. He also owned a string of breweries, which he used the pressurized containers therein to do a lot of his scientific experiments. He was knighted in 1866 for working on the transatlantic telegraph project so that it could send signals across the Atlantic for the first time. He also did a lot of work involving navigation and maritime practices. But what did he do? Well, we've already talked about a little bit, mentioned Celsius and Fahrenheit, and these are two different ways of measuring temperature. Kelvin came up with a third. Over here, the Kelvin scale. So Celsius, which is pretty much my favorite civil temperature measure, is essentially the same as what's referred to as centigrade. And this is calibrated to the chemistry of water. So at 0 Celsius, water freezes. At 100 Celsius, water boils. I like this for civil use because at 0 Celsius I should expect ice outside, at 100 Celsius I'm dead, which I feel is quite a nice gauge. If we translate this to Fahrenheit, which is where most civil temperatures on things like the news tend to get quoted in this country, water freezes at 32 Fahrenheit and boils at 212. Now, if you like Fahrenheit, that's a matter of personal choice. I personally find that this is rather illogical and is kind of based on the temperature of human blood. So it's a scale you can use. I personally will stick to Celsius, or more scientifically, Kelvin, as our class continues. So what Kelvin did was come up with a new temperature scale. And this temperature scale translates to Celsius and Fahrenheit in these ways. So 0 Celsius, or 32 Fahrenheit, is 273 Kelvin. Water boils at 373, and down here at 0 Kelvin was Kelvin's big discovery, and this is absolute zero. So what Kelvin really did was find a temperature and relate that to the thermal motion of the particles in that system and say at what temperature does all the thermal motion stop. So he performed his experiments and found that the temperature at which all thermal motion, when you've removed all thermal energy from a system and those particles will not move around due to heat input, was negative 273 Celsius or negative 459 Fahrenheit. And he called this his absolute zero, his 0 Kelvin, and calibrated his temperature scale to this 0 point. This means scientifically that if you have a temperature in Kelvin, you actually have a measure of the thermal motion or thermal energy of your system. And this is extremely useful when we're trying to calculate how much energy not just a system contains, but how much energy an individual particle has. So for calculations, unless they're civil and actually say find Celsius, find Fahrenheit, our calculations generally will revolve around using Kelvin. And you need to make sure that you can convert between primarily Celsius, but maybe even have an idea how to go from Fahrenheit into Kelvin. So absolute zero is the point where all thermal motion stops. We still have our water freezing and boiling points at 273 and 373 Kelvin, and on the upper end here you can see hydrogen fusing. So these are 10 million degrees or something like that. This is the sort of temperature you should expect to find at the core of a star like the Sun. So let's talk about these scales a little bit more. As I said, the Fahrenheit scale exists. This is a temperature scale based on the temperature of human blood and gives the freezing and vaporization of water at 32 Fahrenheit and 212 Fahrenheit. Why do we use water? Well, water's ubiquitous on the Earth. It's everywhere. And not only is it everywhere, it's also quite an essential feature of life. And our ecosystem really revolves around it. Snow, water, rain, ice, those sort of things really relate to these temperatures. We have the Celsius scale, 0 relating to the freezing point of water and 100 relating to its boiling point. So this was really Kelvin's starting point. He had these two scales. The scale came up that Anders Celsius came up with and the scale that Fahrenheit came up with. And this is what he was working with. So Kelvin decided he wanted to find this point where all thermal motion ceases. But getting to absolute zero is very, very difficult. Requires a lot of freezing and is still something we haven't quite attained yet, although we've got very, 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 very close to doing so, using lasers, for instance, to actually hold atoms steady. So what was Kelvin doing? Well, he had a cylinder with a movable piston in it. And what he did was change the volume of the inside of this cylinder by moving this piston up and down, and look at how this affected the temperature of his system. This means he could make a VT graph, a volume temperature graph, and plotted his points on this graph. This gave him a nice linear relationship. So here's a pressure temperature graph, typical for one of Kelvin's experiments, and he found that for different gases, ideal gases this is, we'll talk about these as we go, for different gases he would end up with different slopes on these lines. What he did was take these lines back and extrapolate them past 0 Celsius here, all the way to some point where they would all intercept. The intercept of all these lines should be the point at which all thermal motion ceased, what he referred to as his absolute 0 point. This is what he called 0 Kelvin, or negative 273 Celsius. Here's 0 Celsius over here. And that is why we have this value of 273. Here's his 0 point, and here's the freezing point of water at 273. So he did this for different gases. They all gave different lines, different slopes, but the same intercept, and his intersection at negative 273 Celsius is what gave him Kelvin. Something to point out is that when you look at Celsius and Fahrenheit, they are actually divided into degrees. So when we're looking at degrees, this is sort of an arbitrary division that people made in order to make their scale. Kelvin is an absolute scale, so you don't say degrees Kelvin, although you find even a lot of professors will do so, or sometimes it's a bit of a slip. But there's no actual degrees Kelvin because it's an absolute scale. So we have 0 Kelvin, or quote any temperature in just Kelvin. So that was what Kelvin did. So there's just a table comparing our water freezing, boiling points, and the values of absolute 0 in Kelvin, Celsius, and Fahrenheit. So if you are doing an experiment in the lab, or you're looking at the weather on the news or looking at any other source, quite often you will not see temperatures quoted in Kelvin. Scientific sources use Kelvin very frequently in physics and chemistry, and even biology in some cases. But you won't see those quoted in a civil sense. You'll usually see a Celsius or a Kelvin. And that means there are conversion factors you would have to apply in order to get your values in Kelvin to do your scientific calculations. Now, to go from Celsius to Fahrenheit, here degree C will be 5/9 times Fahrenheit minus 32. And if we reverse that, we can go from Fahrenheit to Celsius. So F would be 9/5 times degrees Celsius plus 32. I generally won't give you any values in Fahrenheit. I may give you Celsius and I may give you Kelvin, but I will not really go into Fahrenheit. If you want to get to Kelvin from here, you could convert your Fahrenheit to Celsius and then to Kelvin if you're presented with Fahrenheit values. And if you like to think in Fahrenheit, as many people do, then it can be quite useful sometimes until you're used to the numbers to convert your Kelvin into another temperature system that you like, be it Fahrenheit or Celsius, just to make sure for your own sanity that you're actually getting numbers that are sensible. If you get something like 2,500 Kelvin for the temperature of a cup of coffee, you'd probably be quite wrong. Converting that into Fahrenheit might help you understand that. So if we were to do a couple of conversions here, we can convert 256 Kelvin to degrees Celsius. The temperature of Celsius will be 256 minus the 273 Kelvin. We'll get negative 17 Celsius. I would like to point out at this point that the degrees in Fahrenheit are different to the divisions in Celsius. But a 1 degree of change in Celsius is equal to 1 Kelvin change. So a change in temperature in Celsius is the same as a change in temperature in Kelvin, even though the absolute temperature is different. That is not true for Fahrenheit. If you have to figure out a temperature change in Fahrenheit, you must convert both values, then subtract them. If you want to figure out a temperature change in Celsius and convert it to Kelvin, then you can simply take the change in Celsius and convert that to a change in Kelvin. Go the other way, we can take our negative 17 Celsius, and this is really a practice in converting these values. We saw in the previous slide what the answer really should be. Take negative 17 Celsius, add 273 now, you'll get your answer of 256 Kelvin that we had in the previous slide. Let's take the same negative 17 Celsius and convert this to Fahrenheit. So applying our conversion, Fahrenheit will be 9/5 degrees C plus 32, substitute in the negative 17, and you should end up with 1.4 Fahrenheit. So those are the temperature conversions. Like I said, I may ask you to convert between Celsius and Kelvin quite frequently, and a lot less from Fahrenheit to Kelvin or Fahrenheit to Celsius, but you should be aware of how these things are done. So we've discussed gases, and we've discussed liquids, and we've discussed solids. We want to discuss a little more how we can use these thermal properties, or how the thermal properties of a material will be affected by thermal energy, by heat. So if we take a look at these rail tracks here, these tracks have actually been anchored at either end. So if they expand, they actually have nowhere to go. So what's happened here is the sun has beat down on these tracks and increased the temperature of the steel in the tracks. This has resulted in the length of the tracks actually changing. Because both ends of the tracks are anchored to the ground, that's resulted in these tracks becoming buckled and ended up with these S-waves in them, which, from an engineering standpoint, makes these rails kind of useless. If a train were to actually come down these rails and hit this, I think we're looking at a definite derailment of that train and possibly the loss of somebody's house up here as the train goes through it. So from an engineering standpoint, the expansion of a material when it's heated can actually be a very positive thing if you use it to your advantage, or a very negative thing if you didn't want this to occur. Likewise, instead of just having expansion when something is heated, if you cool materials down, they tend to contract and reduce in size. We'll talk about the effects of this a little more. So, right now in the world, lots of people are taking their temperature. You've probably had your temperature taken to get into the class. You've probably had your temperature taken far more than you really want to. I know I have, and I'm kind of tired of it, but there we go. So let's pick on thermometers. So a thermometer, a physical thermometer here, not an infrared one or some kind of thermal camera, which we'll talk about later. A physical thermometer is any device that will undergo a change when subjected to a temperature. Well, a temperature difference, I should say. This means if you take something like mercury, as used to be in old thermometers, or alcohol, you can actually heat them, and as you heat them, they will expand and they will rise and they will reach different divisions on your Celsius, Kelvin, or Fahrenheit thermometer. This can also be achieved if we look at something like carbon. And electronic thermometers often have a resistor inside them that will actually be heated, and the expansion of the carbon in there will change the resistance, the electrical resistance, which again we will come to later in the class and discuss more, will change the electrical resistance of that piece of carbon, and the change in resistance as it's hooked up to a battery will tell you how hot or how cold your system is. So thermometers take great advantage of the change in a material with different temperatures. So thermometers are really designed to use this and designed to measure temperature. And here is an example of an electronic thermometer here. So this would probably have a carbon resistor in here, and as it's heated or cooled, the resistance will change. This is hooked up to a battery. It will measure that resistance and give you, hopefully, a nice healthy reading that allows you into class. One of the most common examples of one of these thermometers is the kind of thing you might see in an older thermostat. And these really use what's referred to as a bimetallic strip. So you could use liquid in glass, as we discussed, or this bimetallic strip method. And what this is two metals of different properties, different thermal properties that expand at different rates. And these are actually welded or stuck together in some way, and then heat is applied to them. This causes one of the two metals to expand more than the other. And as we saw with something like the rail tracks, this will actually cause them to bend in one direction versus another. And this can trip a switch or hit a sensor and actually be a fairly good measure, if you use the right materials, as to what the temperature is in any particular room. And here's one of these systems in action. Here's a bimetallic strip coiled up into a spring formation, and if you apply a lighter to it and heat it up, you can see that it will coil and uncoil, and then eventually, as it cools down, return back to its original position. So as I said, this can be quite useful. If you are in usually an older apartment or house, you'll have these kinds of thermostats which will have some kind of dial that you can turn. And this usually has this bimetallic strip inside it. And the different rates of expansion of the two different metals will cause a switch to be tripped to switch on your thermostat, to switch on your heating at the specific temperature that you set this at. So as I said, here it is in writing, two different metals bound together that expand at different rates when heated. And there it would be if it was a switch. Here we have a bar and a specific length. As it's heated, this bar will extend and trip a switch. That means that solids can expand and contract at different temperatures. Excuse me. So solids are not stuck in one dimension. If you buy 20 feet of steel, you might get 20.3 feet of steel under the right circumstances. So here's a metal bar at some length, which we'll refer to as L, at some temperature T. And it's usually the longest dimension that we talk about most. So we might see volume expansion. I'll mention this as we go, but right now let's look at length. So here we are at length L, temperature T. If we take our temperature and then apply heat to this, so now T plus delta T, so our temperature has increased, temperature plus a change in temperature, we'll see a change in the length of our piece of metal here, our piece of steel perhaps, of length plus delta L. Different materials will have a different response to being heated. So the amount of delta L, how much your material will change in length per degree of temperature, is something that you need to know. And quite honestly, that's usually in a formula, in a table, and usually referred to as the coefficient of expansion or coefficient of linear expansion. And here's some typical materials that you might see in the lab or see in a manufacturing process. Aluminium, because there should be an I in it, brass, copper, gold, blah, blah, blah. Here's concrete, brick, all the kind of things that you see things like bridges built out of, and then you've got liquids and gases here. These coefficients here, I don't expect you to memorize. In an exam situation, they would be given to you, but have an idea as the kind of values you should be seeing. These coefficients are here on a 10 to the negative 6 inverse Celsius here. So these are very small numbers you should expect to see. And there's two columns here. This is a coefficient of linear expansion. This is an alpha, and this should be used when you're talking about a change in length with temperature. Here we have a coefficient of volume expansion, which is given as beta and is inverse Celsius again. Still the same order of magnitude, but this here should be about 3 times this value. That's because this is an expansion in 3 dimensions, it's a volume expansion, and this is a linear expansion just in terms of length. So make sure when you're looking at a problem, are you talking about length or are you talking about volume? And you might have to go and look up a specific value of either alpha or beta to continue your problem. So if it looks like you're missing a value, think about it and say, do I need a constant? If so, which one? So when we talk about thermal expansion, we looked at things like the rail tracks, which would have catastrophic failure due to their expansion, and we looked at things like the thermal change of materials in a thermometer, like a bimetallic strip, where we can use that. But quite honestly, in terms of thermal expansion, this is something you really have to look at if you are a civil engineer or something like that, or you're building any kind of device that's going to be exposed to a range of temperatures that has to be reliable. So if you are driving across a bridge and you see these metal plates that you bump over, don't complain about the engineer putting them in here and bumping you and making your suspension jar up and down. These are thermal expansion joints and are extremely useful to stop this from happening. So if you think about something like a bridge, it will actually experience extremely high temperatures during the day and maybe very low temperatures during the night. Over a season, especially in places here towards the north where we see large changes in temperature, so things can get very, very hot and then very, very cold during the winter, you will see big changes in the overall length or volume of your structure. So this bridge would be built out of concrete and out of steel, and that concrete and steel, if we go back to our previous slide, you can see has coefficient of linear expansions of 12 times 10 to the negative 6, and for concrete and brick about the same. This is why reinforced concrete with steel bars through concrete works so well. But they still expand and contract by some value when they're exposed to differentials in temperature. And this means that if you don't have some kind of joint to allow for this expansion and contraction, you will probably see mechanical failure and the collapse of your bridge or whatever other device you're looking at. So we already said when we talked about thermal expansion of solids here that atoms are in constant motion and the vibration increases with temperature and their spacing increases with temperature. And this is why we end up with a change in our length as we increase our temperature. So let's quantify this linear expansion and find out how much of a length change we'll get for a specific change in temperature. And this is dictated by this equation of delta L is equal to alpha L0 delta T. Here, delta L is our overall change in length. Alpha is the coefficient of linear expansion, one of those alpha values we saw from the table in the previous slide that will apply to your material. L0 is the original length of your object, and delta T is the temperature change. So to conduct this particular formula to find delta L, you will have to take the maximum and minimum temperatures and find out what your overall change in temperature is. So let's apply this a little. Here we have a suspension bridge that's 200 meters long at 20 Celsius. If the exterior temperature varies between negative 30 degrees C and positive 40 degrees C, what range of contraction and expansion is possible? So, we can use linear expansion here for both winter and summer cases, and we can figure out how much delta L, what's our total change in length. So when you're doing these problems, it's good to make sure that you're understanding what's going on, and rewriting the problem never hurts. So here I've rewritten the problem for my own benefit. 200 meters, we've got 20 Celsius, and we've got our temperature extremes. I've also got here the fact that it says a steel bed of the suspension bridge. So I've also got here alpha of 12 times 10 to the minus 6 inverse Kelvin. This is the coefficient of linear expansion for steel that you would need to look up to do this problem. This was not provided in the problem, and if you go back and look at the formula, sometimes you might not have all of the pieces to actually put the substitution together. So finding alpha may sometimes be your own responsibility, either from a formula sheet or from a book in an assignment. So first of all, let's figure out what delta T is. Delta T is our total temperature difference, and we're going from 40 Celsius to a negative 30 Celsius. So our delta T overall is 70 Celsius. Remember, the divisions of degrees in Celsius are the same as the divisions of Kelvin. So a delta T of 70C is a delta T of 70K. We're working in Celsius, but this is just a useful point to be reminded of. Delta L, our change in length, is alpha L0 delta T. We just found our delta T, we can substitute in. And what we'll get is 12 times 10 to the minus 6, our constant, times 200 meters, times 70 Celsius in delta T will give us 0.168 meters, or in more normal terms, 17 centimeters, which is a relatively big change in length if we're talking about a bridge that we don't want to fail. That would make quite a bump at the start or end of that bridge if we didn't put in a thermal expansion joint. You may also see cases of volume expansion instead of just linear expansion. And don't worry, you don't have to remember this entire derivation here. But what's really going on is this is the derivation to take your length values, your L0s or your alphas, and convert them into beta values. Basically, alpha, the length change coefficient with temperature, is beta over 3. So if you don't have a value of alpha, but you have the beta value for volume expansion, you can divide it by 3 and get alpha, and vice versa. If you have alpha instead of beta, you can multiply by 3. Generally, if you're asked to do these calculations, you're provided with the constants that you would need. But you can see volume expansion, and of course you could see something like this in a cube of metal or a block of ice, as opposed to just a suspension bridge where we were looking at the relative change in length. So in these cases, if we increase our temperature, we could increase our volume. If we reduce our temperature, we could reduce our volume. And delta V, the change in volume of our system, would be beta, our volume expansion coefficient, times the original volume times delta T, our change in temperature. So here's our system at its original temperature and volume, and here's our system at its higher temperature and higher volume. Generally, of course, materials would expand, so we can see the volume increased with increasing temperature. But essentially, this calculation would be exactly the same as that you would perform for length expansion. So we can see that here's the equation for delta L being alpha L0 delta T. Here's the equation for volume. So if you can manipulate this equation, you can manipulate delta V equation as well. And there's just some typical coefficients of volume expansion values here for quartz through to air. And of course, remember, if this is in inverse Celsius and you have a Kelvin temperature, then you easily convert this to inverse Kelvin. They're equivalent to one another. And that's why Celsius and Kelvin are quite nice in terms of these coefficients. Now, we've spent a lot of time here talking about materials that expand and materials that contract when they are either heated or respectively cooled. Now, when we looked at our temperature systems, we said quite often that these were based on water, the boiling and freezing points. And I want to point out something a little odd, that water is one of these weird things, chemically speaking. Water actually does some odd things and actually expands as it cools and turns into a solid instead of contracting. So while we've been talking about all these materials that abide by a nice rule of getting smaller essentially when they're cooled and larger when they're heated, one of the most ubiquitous materials, one of the things we can find everywhere, actually expands. It's actually due to the nature of water itself that this happens, but it's something to be aware of, that liquid water actually contracts when cooled down to 4 Celsius, then expands until the freezing point is reached, and then when it's frozen, it actually expands by 9%. So, take your can, if you've got a Red Bull or something, and stick it in the freezer to try and cool it down in the hot summer as quickly as you possibly can, completely forget about it and come back for it 5 or 6 hours later, and what you'll usually find is your can has split open and the contents are stuck to the outside essentially. So if you could just put this can in the freezer, the water inside, which is pretty much the bulk of the material inside this can, other than caramel colouring number 5 and sugar, the water in this can will expand and rupture the actual can itself. The volume of the fluid inside the can has exceeded the volume of the can itself. So ice, water ice at least, is a little bit strange in that respect. So water does not follow the pattern that we've been discussing. And as we said, below 4 Celsius, water expands as it cools. This gives us a useful effect that ice actually floats in terms of water instead of sinking. And that means very cold water stays on top. So you end up with ice on the top of rivers and lakes when they freeze, as opposed to at the bottom, where the water is actually colder in some cases. So ice is actually less dense than fluid when we're talking about water. Why? Well, because of its dipolar nature, when we actually freeze water, the crystalline nature of the hydrogen bonding actually pushes each of the H2O molecules apart away from its neighbor and reduces its density. So the distance of the hydrogen bonds is responsible for this, and as it freezes, all of the particulates push apart from one another and the density reduces. This is very much due to the dipolar molecular nature of water. So water is kind of an oddity in the systems that we're talking about. And there's a couple of graphs here showing you how the volume here of 1 gram of water actually changes with temperature. Obviously here between 10 and 100 the scale has been truncated both in density and in terms of volume. So this green graph shows you the density, this orange graph is showing you the volume, and as you can see, density is going down, volume is going up. So one last thing we want to discuss here is what happens when we repeatedly heat and cool a mechanical system. And here we're talking about anything other than water. We're talking about lengths of steel or concrete bridges or springs, for instance. So if we apply excessive force to a body, we can obviously deform it, we can change it, we can bend it. And the limit to which you can stretch any object is referred to as the elastic limit. And the elastic limit is a point when your object will not return to its original length, when it won't go back to that L0. So take a spring in a physics lab and stretch it too far, it won't spring back to its original shape. You've deformed it. You passed its elastic limit and you ruined it as a spring. Its force versus its extension is no longer constant at this point. Why are we talking about this? Well, we want to talk about how forces can be inflicted on an object based on its changing temperature. We're not going to go too much into materials engineering here, but you can find this limit that we just referred to using Young's modulus, going past the elastic limit. How much can we stretch something before it's permanently deformed and won't go back to L0? And this really equates force to the cross-sectional area of a material. So this is kind of an aside that we'll sort of just talk about here. So force over area equals delta L over L. This is how much force you're applying per the cross-sectional area. This is your change in length, and this is the length of your object. Different materials, of course, will have different elastic properties. Rubber will stretch more than steel. That means we can have something called an elastic modulus, or this gamma value that looks like a Y here. It's actually a capital gamma here. So Young's modulus is F over A equals this elastic modulus, which again is something you can look up for whichever material you're interested in, times the ratio of the change in length over the length, which of course is unitless because these would both be in meters. And when we stretch things, if we were to say have something like our bimetallic strip, things like this would experience shear forces, sideways forces that can act on objects. And that's defined as force over area that we saw before, or the ratio of the force at 90 degrees to the face of the object. This means we can also define strain being delta x over x. So this is the change in length over the original length, and this is the force per unit area. So we've defined stress, strain, and Young's modulus. And like I said, I'm not going to spend a lot of time on this, but we can evaluate what we call the shear stress, or the shear modulus, using a shear stress and shear strain. F over A over delta x over h. And I've actually got two spellings of shear here. And what we'll end up with is this essentially being the squeezing force being related to the shear force. And that's when we referred to our thermal expansion. And the reason that we put these joints in, that the stress that these tracks are actually under is related to that particular value that we just looked at. And if we put a thermal expansion joint in here to allow these tracks to expand and allow these tracks to contract, then they won't actually buckle as they have in this picture. So that was kind of a crash course in that, but this means what we can do is really relate our stress to delta L, how much a length change we get with our changing temperature. So we can say F over A here is our elastic modulus here times delta L over L0. Here's our values for delta L that we saw previously, delta L0 alpha delta T essentially. And by rearranging, we end up with an equation that relates F over A, force per unit area, to alpha, now another constant for elastic limit, times delta T. So you don't really need this derivation. This last part is the important part. F over A is equal to alpha gamma delta T. And why do we care about this? Why are we so bothered about stress and strain at different temperatures? Well, when we construct a particularly important machine, such as a very large cruise ship, and then decide to cruise it around very cold waters where there's possibly icebergs, we might actually experience a lot of stress. So all of the metal here on the Titanic, if anyone didn't guess what this was, would actually contract. This means that the entire system is under a great deal of tension. So, if you were to do something like bump it into an iceberg, you may actually do more damage if you do this at cold temperatures versus doing this at warmer temperatures. And that means at warmer temperatures you might just dent the ship and have a small hole, as opposed to having an enormous tear that causes your ship to sink very, very quickly, and the rest of us to have to listen to Celine Dion for about a decade. So, the temperature at which your system is subject to an impact or subject to forces is actually very important. Take the situation of the Space Shuttle Challenger. A very similar situation occurred here, where these solid rocket boosters are assembled in segments with these black O-rings separating each segment. It was found that leaving the shuttle overnight in some rather low extreme temperatures resulted in the fracture of one of these O-rings. This caused heat and flame to shoot out of one of these connectors, and actually be applied to the outside of the external tank. This external tank holds the hydrogen fuel that goes into the shuttle's engines. Consequently, a blowtorch was applied to the side of a tank of rocket fuel, resulting in the loss of 7 astronauts and the complete destruction of the space vehicle. These are the boosters flying out of the explosion, and here's the destruction of the shuttle and the external tank. This was spectacularly demonstrated by Feynman at the inquest hearing on this particular vehicle's destruction, and he sat on the panel and was told by an engineer that the O-rings could not possibly have failed due to the temperatures that they were exposed to. Having a sample of the rubber on the desk himself, he asked for a glass of ice water, soaked the rubber in ice water, and spectacularly shattered it on the desk, much to the embarrassment of the engineer. So let's take a look at one last example. Here we have a steel beam holding a catwalk, which is we obviously do not want to fail and people to fall. So when fitted on a winter day at 0 Celsius, it measured 12 meters in length. Part A asks how much longer is the beam in summer at 32 Celsius. Part B gives us the cross-sectional area of the steel beam and then says how much force would it take to stretch the beam by the length we found in Part A. So what do we have? We have L0, we have T, we have delta T. We need alpha. So alpha for steel, remember this is our coefficient of linear expansion, is 12 times 10 to the minus 6 inverse Kelvin. We realize that this value is in Celsius, but remember the divisions in Celsius and the divisions in Kelvin are identical, so these values are actually interchangeable in terms of alpha. So we don't need to change the units here. We know that delta L is alpha L0 times delta T. Substituting in, we can say here that alpha of 12 times 10 to the minus 6, 12 meters for L0 times delta T of 32. Remember, we're going from 0 Celsius to 32 Celsius. This is 32 Kelvin difference, delta T. That will give us 4.6 times 10 to the minus 3 meters, or 4.6 millimeters. Now, if the beam has a cross-sectional area of 100 square centimeters, how much force is it going to take to stretch the beam by the length we just found? Our 4.6 millimeters. Well, here we have to look at forces. And the force is going to be our elastic modulus times the area, the cross-sectional area, times delta L over L0. So here, we would have to look up this Y value here for steel, or gamma here. So look up this value for steel. This turns out to be 200 times 10 to the 9 pascals. Delta L here, remember, is 4.6 times 10 to the minus 3, and our cross-sectional area is 100 square centimeters. We need to use this value in meters with this value in meters. So we need to convert the 100 square centimeters to square meters, which becomes 100 times 10 to the minus 4 square meters. Our original length, L0, is 12 meters. Substitute in, we end up with a value of 77 times 10 to the 4 newtons, which is quite a lot of force being this catwalk is being exposed to this beam. We know that steel changes length actually by 0.0012% per Kelvin that it's applied to, and here it's about a 30 Kelvin change. So delta T was 32. That means we should, by applying this particular fact, end up with an answer of 4.6 millimeters, which actually works very nicely with the 4.6 times 10 to the minus 3 meters that we discovered in Part A. That's the end of our introduction to thermal energy. We will continue next time by talking about the application of thermal energy to a wider array of systems.